15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us. This is the Space Nuts podcast. I'm your host, Andrew Dunkley. I think I've forgotten to tell you that for the last 100 episodes, but that's who I am. And joining me as always is Professor Fred Watson, Astronomer-at-Large. Hello, Fred.
How are you doing, Andrew? You see, you've got to keep telling people what your name is because otherwise they get it wrong.
I do it on the radio just about every segment because it's the only way I can remember my name at this particular stage in my life. But I haven't been told to shut up because we know who you are, although when I worked for the Australian Broadcasting Corporation, that actually did happen. I got an email one day saying, Andrew, can you stop telling us who you are? We know. So I did stop for a couple of days, and then I forgot who I was and thought I'd better get back to it.
Yeah, that's right.
You kind of develop, when you're in radio, you kind of develop little crutches, little habits.
Yeah.
And that's probably one of mine. I just sort of default to my name as a way of sort of changing subjects. Others have different ways of doing things. I work with a fellow at the moment who's been in radio even longer than I have, which makes it a very long time. And he has a crutch that he uses when he wants to finish off explaining something. He always ends the sentence with, and all that sort of thing. And I didn't realise how much he said it until somebody pointed it out one day, and now that's all I hear.
Yes.
So anyway, it's like saying to someone, next time you listen to the radio, listen for the breaths between sentences. And then that's all they can hear. People don't notice it until you say something, and then they just can't unnotice it. Anyway, Fred, that's beside the point. Let us talk about what's happening on today's program. And there's been this amazing image released of Jupiter. It's an infrared image, and it is spectacular. Not only that, it was a photograph by a friend of yours, a former colleague, and it is a composite photo. It's not a point and shoot, oh, there's a good photo type of thing. This actually took a bit of work, and it's been going on for about a year. We're also going to talk about catching interstellar asteroids like the Space Doogie. Oh, I got to say it again. Yay. The Space Doogie. A year or two back sort of skirted past Earth and the sun, and we found out after the fact that it wasn't actually from our solar system or even our galaxy, as it turns out, I think, or was from another star system within our galaxy. I can't remember, but Fred will correct me. But now they're talking about a very clever way of capturing these things. I don't know if they mean catching them and bringing them back to Earth or just, finding them. And we've got a couple of intriguing questions to tackle this week. One is related to asteroids and a new theory on the Tunguska episode, which saw vast areas of Siberia obliterated by what was thought to be an asteroid impact. But now there's a new theory thinking that it was an asteroid that grazed our atmosphere. So someone's sort of come up with a question about, well, how close is too close? Well, obviously, if that's what happened at Tunguska, that was too close. And we have Paddy from Sydney, who's a roof tiler, who wants to know if he can go to Mars and put tiles on the roofs of dwellings on Mars to protect astronauts. It's actually an interesting question to ask. So we'll tackle all of that today. We're sort of coming out of left field in many respects, as always. Fred, let's talk about this fabulous photograph of Jupiter. I'm looking at it right now. It is amazing.
It's stunning, isn't it? And what's really spectacular about this picture is that it was taken from a ground-based telescope. In fact, the Gemini North Telescope, which is on Mauna Kea, the mountain in the Big Island of Hawaii. You mentioned a friend of mine a minute ago. He didn't take this image, but he pioneered the technique that has been used to take it. He's now, now retired, actually. His name's Craig Mackay, and he's was for many years a senior astronomer at the Institute of Astronomy in Cambridge. So he, many years ago, addressed the problem of how we eliminate the distorting effects of the Earth's atmosphere. This is, with a big ground-based telescope, the limit as to how much detail you can see in an image is always the atmosphere. It's the turbulence in the Earth's atmosphere. And that's why big telescopes are built on high mountaintops, because they are better.
They've got less to deal with.
Less to deal with, and the turbulence is usually lower, especially if they're near the western seaboard of a continent. There's a complex set of geographical circumstances that lead to this, stability of the atmosphere, which is what it's kind of the holy grail of visible light or optical astronomy. So Craig's idea was, well, let me just say that the sort of standard way of dealing with this is something called adaptive optics, where you look at the light that's coming down to your telescope through the atmosphere, and you sense the distortion in it from the atmosphere by looking at the way a particular star changes. It's actually technically it's the wavefront that's changing, but you can think of it as the twinkling of a star, and you can sort of measure that, you can sense that, and then a little bit like you do with noise cancelling headphones, you essentially invert that signal of the turbulence and basically subtract it from what you're getting, and it cancels out the turbulence. That's the theory. It's a lot more complicated than that, but that is expensive. The technology has taken 20 years to get to the kind of state it is now, which is actually really pretty good. And it's one reason why we're now thinking about building ELTs, extremely large telescopes, on the ground, because they will use this adaptive optics technology. But Craig Mackay, it's probably 20, 30 years ago now, figured that if you've got bright enough objects, you can do something a little bit different. His speciality was what we call CCD imaging. That's the solid state images that are now in all your phones and cameras and things like that. That allows you to, if you've got a bright object, to take many, many images repeatedly of the same thing. And that it effectively gives you a movie. But what the movie is doing is recording, as well as the object you're looking at, it's recording the turbulence in the atmosphere. And there will be moments when that turbulence settles down, and you've suddenly got maybe a tenth of a second or a thousandth of a second of perfect stability. And so what the lucky imaging technique does is you gather thousands of images, and then you go through them and just pick out the ones where the atmosphere was perfectly stable. And then you add those together and you get something like what we're seeing with this image of Jupiter, something that's got the most incredible detail in it. Now, there is a lot more to it than that, as there always is. That should be my crutch, shouldn't it? Oh, there's more to it than that. But the technology is not just, it's not just somebody looking through it by eye. There are very sophisticated algorithms that let you select the best images and add them in a particular way. And in fact, with this image of Jupiter, the algorithms had to be clever enough to allow for the rotation of Jupiter. Jupiter rotates on its axis once in about, it's 10 hours, I think, roughly. And that means that, the features that you're seeing are changing position on the disk of Jupiter. So it's got to take care of all that. So that's how this fabulously detailed image was made. In fact, in Jupiter's southern hemisphere, the detail that you're seeing is almost comparable with what we're seeing from the Juno spacecraft, which is in orbit around Jupiter, right next door to it.
Wow, that's a big call.
Yeah, well, look at it. Just look at the image. You've probably got it in front of you.
I have right now, yeah.
You can see those eddies and whirls, the storms. Yes, it's certainly not the same as Juno, but it's revealing things that we didn't see before in ground-based images. The other thing we should say about this image, Andrew, and I think you've mentioned already that it was taken in the infrared region of the spectrum, the redder than red part of the spectrum, where we're essentially sensing heat. So the reason why the image looks really peculiar when you compare it with a visible light picture of Jupiter. In visible light, the cloud belts of Jupiter are bright, and they're the features that you see most obviously. But in infrared, the cloud belts are actually dark because they're silhouetted against the heat that's coming out from the planet's interior. So what you're seeing in the bright regions of this image and it is easy to find. I'm sure our listeners will go and find it very easily. But
they'll see it when they download the podcast, because I'm going to make it our feature image for this week's episode.
That's the thing. Yeah, good. Okay, so we can talk about it with impunity. We don't have to worry that people are going to say, "Where will we find this image?" Yes. So yeah, it's the cloud belts are dark, and in between them are bright regions. So you're looking down to the layers of Jupiter's atmosphere that are warmer than the cloud belts, and that's why we see this effect of the cloud belts being silhouetted against this heat radiation that's coming from Jupiter itself. A marvelous image, really, and very, very spectacular. And I hope Craig's looking at it and thinking, "Yeah, I started all that a long time ago."
Yeah, it's nice to sort of be a pioneer, I guess.
He was, yeah. And,
that's what Captain Cook told you when you came to Australia, isn't it, Fred?
Something like that, yes.
Yeah. With an infrared image, I'm just interested to know, and it's a silly question, but what colour is the red spot in an infrared image?
That's a really good question, and I don't know the answer to that. I'm not sure whether the red spot might be in this image, actually, but silhouetted.
I'm suspecting it's black.
It's colder, yes, that's right. The red spot does, we know from Juno that the sort of circulation, it's a big cyclone, and that extends a long way down into Jupiter's atmosphere. So you might expect that you're seeing a bit of a hole into the lower layers of Jupiter's atmosphere that might make the red spot bright. But of course, the red spot needn't necessarily be on the side of Jupiter that's facing us in this image. But you've got me there. I shall try and find out. That's a really good question.
No, well, I didn't think it was. But anyway, thank you. I'll take that.
There's another thing that we might just mention, and that's that the infrared radiation that is detected from objects in space is not just one color. It has a spectrum, like visible light does. So you can see, these sort of barcode features in the infrared spectrum, not as many as you see in visible light. But you can also divide the infrared spectrum into color bands, which we do, and we call them J, H, and K, at least in the near infrared, which is a bit odd because they're not in alphabetical order. The J is not, it's just wavelengths a bit longer than red light, and K is much longer, and K is where the K waveband is where the heat really starts showing through. So I suspect this image is either in the K waveband or in perhaps a composite of some of those wavebands.
So now that we've sort of perfected this technology and we're able to gather images of our near neighbours like this, is this going to mean that it's probably going to be easier and somewhat cheaper than sending probes to other worlds, or are we still going to have to do that for practical purposes?
Yeah, there's no question but that you learn more about these distant objects by having something right next door to it. You can do so much more. Images like this are they're valuable because they actually back up what the spacecraft are telling us. So, you can bet there'll be scientists comparing this image with the images that were taken by Juno at the same time, showing the clouds in the same instant of time. So all of this comes together to increase our knowledge. There'll be researchers who are getting the most amazing information out of this, but you also need the spacecraft. There's no question of that.
And I suppose that also backs up the basis of scientific discovery. You need more than one confirmation.
Yes, that's right.
To determine something, don't you?
Yeah, that's right. That's the element. The central element of science is that you need to be able to do repeated experiments. You need to get information from different sources.
There you go. All right. Take a long, hard look at that beautiful image of Jupiter, which is on our website and probably on whatever image you're looking at via whatever platform you download our podcast from, which is sort of available everywhere these days. You're listening to the Space Nuts podcast with Andrew Dunkley and Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, before we get on to our next topic, I'm very excited to be able to tell people that want to ask us questions that they can do so. Now, up until now, we've been getting questions through Facebook posts, through email, through the website contact interface, but now you can record them. If you would like to record using your own voice or someone who sounds similar to you, a question for us, you can go to our website and there is a start recording button. All you have to do is have a microphone available through your laptop. I guess it'll work through your smart device, whatever. And once you're geared up, just press start recording and away you go. You can ask us your question. We'd like to keep questions down to 10, 15 minutes max, or 10 or 15 seconds even. But even if you have something you want to say or something you want to ask Fred about, you can use the recorder. Now, it's available through the bytes.com Space Nuts website. So that's bitesz.com/spacenuts, bytes.com/spacenuts, and you can record a question. And if we deem it worthy, Fred, we will use the audience audio rather than me reading out questions from people third party. So it'll be a nice new toy for us to play with, a new innovation, and it'll give people an opportunity to hear from other Space Nuts listeners in their own voices, which I think is a fabulous thing. And we'll be able to answer the questions that way. I mean, we'll still take them the traditional way in writing or via email or whatever. But if you'd like to record a question, that is available right now on the bytes.com/spacenuts page. Now, Fred, looking forward to that, by the way. Let's move on to our next topic, which is that of catching interstellar asteroids such as the Space Doogie or Oumuamua, as it is officially known. When they say catch, are they talking about finding or actually capturing?
Neither.
Right. Okay. I knew I'd get that right.
Yeah. So they'll be found by telescopes on Earth. And in fact, the one that will probably do the biggest job in discovering interstellar asteroids, these are asteroids that come from another solar system, that will probably be the Vera C. Rubin telescope, formerly known as the Large Synoptic Survey Telescope, which will be online in Chile in a couple of years, I think. That telescope is going to survey the whole sky, or the whole southern sky, I think about once a week. And so it will be second to none at finding asteroids, not only near-Earth objects that might one day collide with the Earth, but also things that come from other solar systems. So the finding will be done in a sort of routine way. The problem that has been recognized with the two interstellar visitors that we've had, and one, as you rightly said, was the interstellar asteroid Oumuamua, which I always think of as more like a French breadstick than what you always think of, but that's just the way these things go. It's a long and thin, that's the bottom line. And the other one is Comet Borisov, which is actually has now passed through the solar system, but was very exciting at the beginning of the year. The problem with these objects is that first of all, they're incredibly interesting because they're free samples of the constructional debris of other solar systems, which is a very exciting thing to find. But the problem is that they are typically whizzing through the solar system at speeds that make them very difficult to catch. So the idea of grabbing one of these and bringing it back is not one that's on the horizon at the moment. But what we would like to be able to do is to take a better look at them, either by a flyby of one of these objects with a spacecraft, or better still, a rendezvous where you put a spacecraft into orbit around one of these objects. The problem, though, is actually setting the scene in order to be able to do that. And, we felt very impotent, particularly with Oumuamua. I think Elon Musk tried to drag together enough rocket-powered oomph to send something chasing after it, but it it really wasn't going to happen. This thing was herring off at 23 kilometers per second or something.
It was long gone by the time we found out about it, wasn't it?
Well, it was past its closest point. That's right. So that was very much a rearguard action, trying to figure out how to send something to chase after it. So a suggestion has been made that we should be better prepared, and it's been made with sufficient quality and cogency that the NASA Innovative Advanced Concepts Program, the NIAC program, has actually funded research into how we might deal with this problem. And the suggestion is to build and put into orbit around the sun something, and I love this name, something called statites or statites, and it's short for static satellites. Okay. And they're satellites of the sun, not in orbit around the Earth. So what you do is you build these things. You equip them with light sails, which we've talked about before as well, and what the light sail, and then you send them out to various strategic points in a ring around the sun, effectively. I don't know how many you would have. That would depend on the funding and things of that sort. But the light sails actually act as stabilizing devices, so they basically allow them to hover in the same spot in the above the solar system, if I can put it that way. They would probably also have the capability to detect smaller objects whizzing past, so they might, if you're in the outer solar system, you might see something that has not yet been picked up by the Large Synoptic Telescope or the Vera C. Rubin telescope, so that there is a detection capability. So I'm sorry I made that error when we spoke, when we described this a minute ago. So yes, finding them is part of the deal. Although I think we'll still find that most of them are found from Earth-based telescopes. Anyway, that's the first part of it. So you've got these things in a ring, but then what you do is you have each one of them has its own little fleet of CubeSats, and so if something passes reasonably close by, you can essentially launch off a CubeSat to chase after it, and either do a flyby or do a rendezvous, go into orbit around the object. It's a really neat idea. It's a very, very clever suggestion. It's led by somebody called Richard Linares, I think his name might be. He's in the Department of Aeronautics and Astronautics at the MIT, the Massachusetts Institute of Technology. So fantastic stuff. And what a great suggestion. I don't think it's anywhere near being on our immediate horizon, because this is only a feasibility study. But yeah, maybe in a few years, we might find that we've got this ring of what somebody has described as solar sailing sentries. Love the alliteration there.
That's clever.
Yeah, good stuff.
It's a very clever idea. It's probably not a simple task to execute, but if they're smaller objects and easy to manufacture, that makes them easier to launch and deploy, et cetera, et cetera.
Yeah.
And really an opportunity to learn a hell of a lot about what's happening beyond our solar system, which, let's face it, is one of the great mysteries, isn't it? We can see out there, but being able to actually observe something that's come from out there that's in our vicinity would be wonderful.
Exactly. And just imagine what, if you think back to when Oumuamua flew through the inner solar system, which I think was the end of 2017, if I remember rightly. It's quite a while ago.
Yeah, it was. Yeah, I think so.
But imagine if we'd had something like one of these that was sort of ready for it, and could launch a CubeSat to chase after it, or even intercept it. As it leaves the solar system. It doesn't really matter where you intercept it, as long as you get close to it and get close enough to give us some images, rather than our imaginations, which is what runs riot in the case of Oumuamua. Fabulous stuff.
Indeed. And probably no truth to the story. I heard that Oumuamua, affectionately known as the space doogie by all the world's leading experts, is the reason why there's a toilet paper shortage on Earth
that
at
could
the present
be it.
time.
Yeah.
That'd be it. Yeah, nothing to do with coronavirus. But, yes,
Right.
just this big thing that
Indeed.
flew past.
You don't need to go into detail, Andrew. We get the
Don't I? Oh, I was going to elaborate.
Yeah, I thought you might.
don't need to do that. Good. Okay.
No,
Well, that saves a bit of explanation, doesn't it?
I think we need.
You're listening to this.
We should
Go
bring
on.
the conversation to an end with the classic and that sort of thing.
Yes. And speaking of which, I mean, we're talking about people's catchphrases or crutch phrases earlier on. Yours, Fred, I know, is, and the reason this is in the news at the moment. That's yours.
All right.
I'd like $1 for every time I've heard you say that.
Yeah, it does come out a lot. I kind of like to explain why we're talking about things.
Yes.
Does it? Perhaps it doesn't.
Well, quite often what we talk about requires a backstory so we can talk about what's developed today. So that's how it goes.
So I'm looking forward to being able to say, and the reason why that isn't in the news at the moment is...
Well, I'm looking forward to saying that when it comes to COVID-19.
Yes.
The reason why that isn't in the news is because we defeated it.
Yay.
Yeah, it'll be a long way off, though. You're listening to the Space Nuts podcast, episode 202, with Andrew Dunkley and Professor Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments, and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, yeah, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Now, Fred, I always like to shout out to our patrons through patreon.com/spacenuts, the people who are putting their money where our mouths are, which we really appreciate. And because of that, we've been able to invest in some new toys, such as the voice recorder on our website, so people can basically ask the questions of us verbally without having to write emails and messages. But we have a new opportunity for people, again, driven by the audience. And this is, I suppose, similar to Patreon. It's just a different platform called Supercast. Now, a lot of people prefer to use Supercast or have a preference for Supercast. So we've set up an account on Supercast. Spacenuts.supercast.tech is the website. Spacenuts.supercast.tech. You'll probably find a link to it on our webpage. But there you can become a premium member of the Space Nuts podcast, and it's $5 a month. There's a 30-day free trial, which you can cancel anytime. And you get access to our back catalogue with new episodes added weekly, exclusive bonus material, 100% commercial free. So that's what we offer you as a Supercast member. So you might want to check it out, spacenuts.supercast.tech. Now let's get into some questions, Fred. We've got a couple of interesting ones, as always. And our first question comes from Camelo, who is in Los Angeles. Now, Camelo introduced himself by explaining that he is a social worker in LA and he's looking after the homeless on the streets. And pretty busy time of it at the moment, trying to help them not only to survive day by day, but avoid COVID-19. So our hats off to you, Camelo. You're doing amazing work, and thanks for getting in touch. And we wish you well with everything you're dealing with at the moment. People like you make the world go round. I work for the Salvation Army, so I do understand where you're coming from, dealing with the welfare needs of people who are just so down on their luck. And Freddie's got a sort of a two-part question, and this relates to what we were talking about in terms of asteroids. So this question was inspired by an article that he read in the Siberian Times. Now, the Siberian Times has come up with a new theory about how the Tunguska event originated. Basically, that thing that happened over 100 years ago that flattened massive areas of Siberia with the shockwave of an asteroid impact. Now, according to the Siberian Times, another theory is that the asteroid didn't actually hit the Earth. It skimmed the Earth and went back out the other side of the atmosphere. So Camelo's asking, how close might an asteroid skim by Earth without crashing into it and or being pulled into the Earth's gravitational field? And how large is the size of the one that would skim Earth versus those that often pummel our planet on a daily basis? Are these things the only deciding factors, or might we also include a factor where it flies by and what that particular part of the Earth's magnetic field looks like? I'm not sure if I'm right, but I do know that it varies from place to place, does it not? Sorry for my long-winded questions, and many thanks for your combined podcast, even though these odd times for us biological creatures on Earth. It's an interesting question about asteroids. I suppose the bottom line is how close is too close, and can they do the damage that we're talking about in regard to Tunguska without actually hitting us?
That's right. I actually saw that article as well, and I think it is a really interesting suggestion. So the idea, and what prompts this suggestion that maybe it was something that basically grazed the Earth, it skimmed through the atmosphere, detonated probably, but then the bulk of it carried on its journey through space. One of the reasons why people like that idea is that it's very hard to find any evidence of debris as a result of the Tunguska event. There's no single crater. People have looked at the whole landscape around there. It's full of lakes, and there is a suggestion of a lump of something at the bottom of one of the lakes, but nothing that would, account for the 80 million trees that were essentially flattened by that explosion, which, if I remember rightly, was in 1908, as I think you mentioned earlier. So if you postulate a grazing impact, then you at least, if you can make the physics work, and apparently they do, you can neatly answer why there's no meteorite, there's no asteroidal debris that has been found in the district. So just going to Camelo's questions, the answer to both of them, and you might not be surprised to hear me say this, is it depends. How close might an asteroid skim by the Earth without crashing into it and or being pulled into the Earth's gravitational field? So what it depends on is the speed of approach. If you've got something that's going relative to the Earth, let me do a quick calculation here, less than about 11 kilometers per second, then it will probably hit the Earth, because that's the Earth's escape velocity, and it works backwards as well as forwards. But most of these things are traveling much faster than that, because the Earth's orbital velocity is 30 kilometers per second around the Sun, and asteroids are in orbits that give them a whole range of velocities as well. So you might get things up to perhaps 70 kilometers per second on the high end, and you can get things that are low speed because you've got the asteroid and the Earth going in the same direction. So it all depends. If you have something going at a really high speed, then it will, and it would skim through the atmosphere, then it will be slowed down by the atmosphere, but not really significantly. And that might be the phenomenon that we've seen with this object. So you get an interaction with the atmosphere that is probably explosive and very likely to cause debris on the ground. But the height that this would happen, I'm guessing that you're talking about heights as near as 30 kilometers or something like that to the surface. That would, if something was going fast enough, it would not be appreciably slowed down by the atmosphere, even at that sort of depth. But it would cause, if it was a big object in particular, it would cause quite a dramatic detonation of the outer layers at least. The thing about asteroid impacts is a miss is as good as a mile. And yes, a miss of 500 kilometers is much better because it doesn't interact with the atmosphere to speak of at all. But if you've got something that penetrates deep into the atmosphere, and I'm saying, maybe 30 to 50 kilometers, I think 50 kilometers is the assumed height of the explosion at Tunguska, then if it's going fast enough, it will keep on going. And once again, how big is the size? Well, it really is dependent on speed. What the size determines is how much of it comes out the other side, the other side of the atmosphere. If it's big enough, then there'll be still something left to fly on back in its orbit. If it's smaller than, and I would guess you're talking about 50 meters or something of that size, then you might get a complete detonation and will produce some debris on the ground, which is exactly what happened with the Chelyabinsk episode back in, was it 2015, as long ago as that, where there was an explosion 30 kilometers above the ground, and there's a debris field downstream of that. The biggest lump landed in a lake. That thing didn't carry on in its orbit around the sun, but basically was thought to be about 20 to 30 meters across. Once you get into the kilometer regime, you're talking about big danger there. There's danger of global impact. The current situation with near-Earth objects is NASA is working very hard, or it's funding observatories at a very high level to determine everything down to a size of about 140 meters. That's the current threshold. Now, something that big hitting us is definitely going to do city or statewide damage, but it doesn't wipe out civilization. So that's the current threshold for objects to be found. I think Congress mandated NASA to facilitate finding 90% of such objects, because it's always a statistical thing. You never quite know where the last one's going to come from.
Yeah, no, I find the whole thing fascinating, and the more we look, the more we find, the more we realise that there are numerous things out there that may or may not be a potential threat, but at least we're keeping an eye on it, and that's important. And as time goes on, assuming we don't suffer a direct hit of something massive, and there's none of that in the foreseeable future as far as I'm aware, we'll get better at finding them and better at dealing with them. And technology one day, if not already, will reach a point where if we've got enough warning, we might be able to do something about it by perhaps diverting it just enough so that it will miss us.
That's exactly the ploy. So just a sort of aside on that, one of the telescopes that kept on working throughout the COVID-19 shutdown is the Pan-STARRS telescope on Haleakala in Hawaii, which is designed to look for exactly this sort of thing, near-Earth objects. So we can be, reassured by the fact that one kept on going. And just as an adjunct to that, I might mention, Andrew, that this very week, the week starting the 11th of May, the Anglo-Australian telescope began work again. So we're observing with the
wonderful
Australian telescope in Coonabarabran. They've started work again with very strict COVID restrictions, of course, but it's hard at work. They got data over the last 2 nights, which I'm delighted to hear.
Wonderful. Also this week, I believe, and it may have been attributable to a meteor shower that we've been experiencing recently, there was some kind of high atmospheric explosion over some part of the United States, which was witnessed and certainly heard by many people. And it's a classic case. They saw it and then they heard it probably, well, the reports are saying 3 minutes later.
Yeah, that's about right. Yeah, I hadn't seen that report. Actually, that's interesting. Yeah, the sonic boom is, 3 to 5 minutes later, depending on the height that it actually explodes.
Yeah, but no damage as far as I'm aware in relation to this one, unlike Chelyabinsk and Tunguska is one of the great impacts or near miss impacts or explosive events in natural history. It's they've actually managed to get photos of the damage of Tunguska, which are worth looking at. But it just laid down vast areas of forest like matchsticks. It was just incredible. Now, let's move on to our next question, Fred. And thanks again, Carmelo, for getting in touch with us. Great to have you on board as a space nut. Now, this is a question from Paddy, who has questioned us before. Paddy's a roof tiler from Sydney, Australia. He's just finished listening to the 200th episode and, sends his congratulations. Thanks, Paddy. And we did answer a question of his recently, and he has another one. So can we ever in the near future, as in 20 years, really send men or women to Mars? Because if we can, they'll need a roof tiler or a roof on their hab. And is terracotta roof tile a good way to block the sun's radiation or solar flares or neutrinos? By the way, I did get an adapter for my telescope from my iPhone 10 and have taken pictures of the moon, Saturn's rings and Jupiter. We'll upload them as soon as but I can't wait to see them, Paddy. Protecting astronauts on Mars is probably the serious side of this question. I'm not sure they'll send Paddy to do roof tiling, but they may. But terracotta being a wonderful product that's used in roof tiling and construction, would it be enough to protect someone on Mars?
I doubt it. Sorry, Paddy.
Suspected you'd say that.
Let me just, if I may, just go back to what Paddy was saying about his pictures of the moon, Saturn's rings, and Jupiter. And you didn't finish the sentence, but he used a technical term there, which I like very much. He said he will upload them soon, but still too much Allen. And Allen, of course, is artificial light at night. So,
okay.
Because Sydney is not the darkest place in the world, although parts of it are reasonably dark. Where I live, we actually get quite good views of the Milky Way from time to time. Never mind.
You should move to a better suburb, Fred.
What, you mean a better suburb where there's more Allen?
yeah, that's what I mean. Yeah,
that's right. So I think I have to say I am not familiar with the radiation blocking properties of terracotta roof tiles. I think they're good at keeping out the rain, probably, which is why they're all over the place. But with the sun's radiation, and these are high-energy subatomic particles, I think you need something more like lead blocks to stop that. Maybe lead sheeting would do it, or certainly something that will slow it down. Terracotta might work, but I think you might need several meters of thickness of it, and that is not kind of what roof tiles look like normally. So I suspect that what we need is for Paddy to maybe do a bit of retraining in heavy lead roofing, and then he might be a candidate for going to Mars. His first question, however, can we ever in the near future, as in 20 years, really send men or women to Mars? I think we will. NASA plan is of order 2035. That's only 15 years away. There are still things to solve, and the radiation hazard is one of them. So it's a great question that Paddy asks. I think what will happen with the first astronaut visits to Mars will be that there will be great precautions taken against the radiation. And it's a problem that's not really properly solved yet, but you can imagine that you might send robotic spacecraft there to start digging holes in the ground that people can, use as their habitation areas, in order to give them roofs that will actually inhibit the radiation risk. It's one that a lot of people talk about. A lot of work's being done about. I don't think we've got the perfect solution yet. You've also got to worry about the 6-month flight to Mars, 6 or 8 months. You're in a very high dose radiation regime then as well, and I don't think the problem of shielding the spacecraft has yet been properly solved either. Although I've seen some ideas. Sometimes they use bags of water and things like that to try and inhibit the penetration of radiation. So we will see what the outcomes of all this are. It's clearly a solvable problem. Whether it's solvable with a spacecraft that can be made light enough to get people to Mars and back is another question. However, it is on the agenda.
Yes, indeed. Lots of problems to solve, but they've got people working on it, and I think they'll ultimately come up with answers. They won't go until they've solved all these problems. There's no point sending people on a suicide mission. And the other problem is lower gravity, so they're going to have to deal with muscle wastage. So I guess a lot of their time will be spent while they're in transit exercising to keep their muscle tone up.
Yeah.
They even did that on Skylab, I remember, and they used to they had a track built around the interior cylinder of Skylab, and they used to just run around in circles in 0G. I saw footage of it, and that was how they exercised. And exercise is very, very important in 0G to stop muscle wastage.
Yeah, that's right.
I imagine it would be critical on a trip to Mars.
Yeah, it would. And that's actually one reason why the International Space Station is there, because it allows us to determine what kind of exercise regime is necessary. And astronauts up there exercise for several hours a day. So it's all about, keeping muscle tone up. Yeah,
well, what else are you going to do besides reading? You might as well exercise. So that's why I'll never be an astronaut. I'm not a prolific reader, and I hate exercise. So I'm off the wait list. I'm on another wait list because of the lack of exercise, but I'm not on the wait list for a trip to Mars. And neither are you, Paddy, I'm sorry to say. I don't think a roof tiler is going to get the gig. But it was a nice thought. Actually, it reminds me when I was growing up, my childhood home had a terracotta roof, and a lot of the moulding they used in those days, in those 50s construction homes, was lead moulding to stop water getting in underneath the eaves and things like that.
That's right. I was just going to make that. Yeah, that lead used to be used. Yeah, interesting. Which would be very, very handy for stopping solar radiation, as it turns out. Thanks for your question, Paddy. Really appreciate it. Thanks to everyone. And don't forget, we now have a voice recorder system on our website if you would like to directly ask us a question using your own vocal cords. We'd love to hear from you. So go to bitesz.com/spacenuts. That's BITESZ. And record your question for us. Hugh, our producer, is waiting with bated breath. We can't wait. Please do. And don't forget to tell us who you are and where you're from. That's important as a part of it. Just start off by saying, "Hi, I'm Fred Watson, and I'm from Sydney, and my question is," and that should cover it. That's Fred's real voice, by the way. Fred, as always, thank you. It's been a great pleasure. It's always a pleasure, mate. It's great to talk to you. Thanks. Honestly, for all I've lived in Australia for, what is it? It's more than well over 30 years. I can't do the accent at all. It's actually...
Yeah, and it's always difficult for someone who's not a native speaker to try and replicate. But then again, I've got a terrible American accent, and after a while it turns French. I don't know why, but if I try a French accent, it turns American. So
there you go.
It's pathetic, really, it is.
Yeah.
Horrible. Thanks, Fred. It's been good fun. We'll catch you again next week.
Sounds great. Take care. Bye for now.
That's Fred Watson, Astronomer-at-Large, with us every week here on Space Nuts, as are you, which we greatly appreciate it. Thank you, and we can't wait to have another chat next week. And from me, Andrew Dunkley, farewell. See you next time on another edition of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.